Okay, here we're looking at question 3 from your workbook. I'm trying to focus this so you can see it. So this is a Hess's Law question, and we're being asked about this first bolded chemical reaction. And sometimes we might want to know the delta H for a reaction. And one way to figure it out is to go into the lab and actually do it. Some reactions aren't that easy to carry out. You see, in this case, we have oxygen atoms, and oxygen in the environment exists as O2. So this reaction, it actually doesn't even have to be a real reaction that you can carry out, but you can still figure out the enthalpy change by using other known reactions and their enthalpies to figure it out. So actually I already did this on this piece of paper, so I'm just going to walk you through how I did it. You might want to pause this right now and just try manipulating these 3 reactions so that they add up to give this unknown reaction. You might want to flip one left to right. You might want to leave it. You might want to divide it by 2 or divide it by 4 or whatever. Whatever you need to do so that they add up to your desired reaction here. So let me explain why I did what I did here. In this first reaction, I left it as is. Why? Because I can see that I need NO on the left. The only NO I have in all of these reactions is in this first reaction, and it's on the left. So I'm going to leave it as is because I have one NO in each place. Okay, so that's going to contribute negative 198.9 to my enthalpy change. Okay, so then I get to the second reaction, and I look and I see it involves ozone. Well, in this first reaction, I had ozone there, but that's not in my final reaction. So I'm going to use this to get rid of this ozone. So I'm going to flip this so that the ozone goes on the right side. So that's why that says flipped. What that's going to do to the enthalpy is it's going to change it from negative 142.3 to positive 142.3. Okay, then in this third one, I just look here and I say, okay, this has 2 oxygen atoms. I need 1 oxygen atom on the left. So I'm going to flip this so that the oxygen's on the other side, the oxygen atom, and I'm going to divide by 2 so that I only have 1 oxygen atom. So flipped and halved. So I'm going to take my positive 495, I'm going to change the sign to negative 495, and I'm going to divide by 2. Okay, so let me zoom back out here so you can see what I did. Actually, maybe, here we go, maybe I can do it this way. So the very first reaction, I left it as it was. And that I'm keeping a tally over here of my delta H's, negative 198.9. Then the second one, I flipped it so that it's backwards, and that gave me 142.3. Then the third one, I flipped it and halved it, so that gives me this value. And so check it out. This said 102, so I put 2 over 2 here just to show you that I can add it to 1 over 2, and that gives me 3 halves. So I have 3 halves dioxygen on the right, and I'm going to cancel that with my 3 halves dioxygen on the left. I'm also going to cancel my ozone. And look what I get. I get NO, O, and NO2 left over. That, if you recall, was our desired reaction. So now I'm going to take out my calculator and I'm going to add up all of these values, and I get negative 304.1 kilojoules per mole. And I'm going to retain my 1 decimal place here, and that is obviously an exothermic enthalpy value. Okay, so now we know So I'm going to try to zoom back out. Okay, now we know the delta H for the reaction we had up here. So our delta H is negative 304.1 kilojoules per mole. Okay, so as we know, we're often going to be using these as a conversion factor. So I'm going to write it like that. And in this question, we're asked, what is the enthalpy change when 2.65 grams of nitrogen monoxide reacts? So this is just like the previous stoichiometry problems we've been doing. We're asked about grams of nitrogen monoxide, and here we know that this is negative 304.1 kilojoules per 1 mole. So what else might we need here if we're going to jump over to mass? Well, we're probably going to need the molar mass. Okay, and then we also have this 2.65 grams given. Okay, so let's go ahead and do a dimensional analysis. Now we're asked for the enthalpy change, so we're going to have this on top at the start of our dimensional analysis. Like that. Now I'm going to go on over to grams using my molar mass. So I've used this and I've used this, and now I'm going to use my 2.65 grams. Note that I'm going to have 3 significant figures. I have 3 here and here. Here I have 4, but I'm limited to 3. So my answer turns out to be 26.9, that's negative, kilojoules, not per mole, but per 2.65 grams.